continue. Welcome to the seminar series on modern artificial intelligence at the NYU Tandon School of Engineering. The series has always aimed to bring together faculty, students, and researchers to discuss the most important trends in the world of AI. And that remains true, even in the virtual format necessitated by the pandemic. I'll start, as always, by thanking Dini Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering, for supporting the series and allowing me to introduce to you a growing list of esteemed speakers, all of whom are world-renowned experts whose research is making an immense impact on the development of new machine learning techniques and technologies. In the process, they are helping to build a better, smarter, more equitable world, and we are proud to bringing them to you. The series for this semester wraps up today with a presentation by Sham Kakada, a senior principal researcher at Microsoft, whose thesis helped lay the statistical foundations of reinforcement learning. It's my privilege to tell you a bit about Sham before bringing him to the stage. In addition to his work at Microsoft Research, he is a professor in the Department of Computer Science and the Department of Statistics at the University of Washington, where he focuses on the mathematical foundations of machine learning and AI. He played an integral part in the development of one of the first provably efficient policy search methods in reinforcement learning, developed the mathematical foundations for the widely used linear Bandit models and the Gaussian process Bandit models, set forth the tensor and spectral methodologies for provable estimation of latent variable models, made the first sharp analysis of the perturbed gradient descent algorithm, and designed and analyzed numerous other convex and non-convex algorithms. He had the honor of serving as program chair for the Conference on Learning Theory in 2011 and is the recipient of the ICML Test of Time Award, the IBM Pat Goldberg Best Paper Award, and the Informs Revenue Management and Pricing Prize. Going back a little further, Sham earned his undergraduate degree at Caltech, where he studied physics and worked under the guidance of John Preskill in quantum computing. He then completed his PhD with Peter Dayan in computational neuroscience at the Gatsby Computational Neuroscience Unit and was a postdoc with Michael Kearns at the University of Pennsylvania. Pardon me. Although he does not list it on his official bio as a music lover, I feel it's worth noting that he is one of the creators of MusicNet, a curated collection of classical music recordings with more than 1 million annotated labels indicating the precise time of each note in every recording, the instrument that plays each note, and the note's position in the metrical structure of the composition. It's a noble undertaking that has provided the machine learning and music communities with a valuable resource for training models and a common benchmark for comparing results. Now, I know you're all eager to hear his talk towards a theory of generalization in reinforcement learning. So without further ado, let me present Sham Kakada.
Thanks, Anna, for the intro. And it's a real pleasure to be here. And this is really just an exciting seminar series. As many of us know, there's been a huge revival in reinforcement learning over the last few years with much recent progress, both from a practical perspective and a theoretical perspective. This talk will be surveying a number of results, including some various breakthrough results over the years, and we'll see how there's really been a lot of progress even in the last year or so. Okay, so why is reinforcement learning becoming so relevant now? Well, it's because many researchers are trying to build technologies which will impact the future. And as machine learning is impacting society more, we're realizing that our deployed machine learning methods are going to be interactive in nature. And this is what the paradigm of reinforcement learning means to study. We're trying to understand how an agent in an uncertain world can obtain some measure of long-term future reward. Okay, so let's start by understanding some of the challenges we face in reinforcement learning. I'll define the paradigm a little more formally later on, but I think many of us are familiar with it at least at a crude level, as shown by this picture. So we've got this agent that wants to get some reward, and it might not know the environment. So the first challenge it might face is the problem of exploration. And on top of that, as the agent is taking actions in the world and experiencing outcomes, we have the credit assignment problem, which is that should the agent happen to hit this -1 reward, it's got to attribute what was the mistake in the past that led to this negative outcome. Okay, because we don't have an expert telling the agent which actions were correct and which ones were incorrect. Okay, on top of this, we've got the problem of the curse of dimensionality, that in realistic reinforcement learning problems, the state space and the action space is often very large or infinite. Like in this recent and impressive demo from OpenAI, and forget about the Rubik's Cube aspect, dexterous hand manipulation is considered one of the most challenging robotic controls tasks. And the fact that they got it to manipulate this cube at all is very impressive. And this is really a reinforcement learning problem with a high dimensional state space. This is the joint angles and velocities, and a high dimensional action space, which is the forces at the actuators in this robotic hand. Okay, so before jumping into the details of the talk, let's bump up a level and go through how we think about generalization and representation in both supervised learning, and then move to RL. Okay, and much of the talk, more specifically than generalization, is going to be thinking about representation. Okay, so this is just really a whirlwind tour of selected results. So let's look at just this representational issue in supervised learning. So, we're all familiar with these neural networks and convolutional neural networks. And the idea is we take some image and we transform it to a prediction. And we might think of the representation as this top layer, that we're taking this image, we're transferring it into some low dimensional representation, say phi of x, and using that for classification. Okay, and we can think of this phi of x as the top layer representation. Hopefully that's low dimensional. Okay, and there's a lot of work down below which turns this image into this representation. And what we've learned from deep learning is that these, at least modern neural network methods, they can often simultaneously learn the representation and the predictor quite well. And once they have representations, they often transfer quite well to various downstream tasks of interest. Okay, so now let's jump into a little more technical viewpoint, again, an overview of how we think about generalization in supervised learning in this IID setting. So suppose we've got some hypothesis class and we just want to find the best hypothesis in this hypothesis class. Okay, and how many samples do we need to do this? Yeah, there's various results for how we think about that. But the bottom line is we really can generalize in supervised learning in this agnostic sense, where if given a hypothesis class, we can find the best one. So the number of samples we need only scales logarithmically in the size of the hypothesis class. Okay, and if a hypothesis class is, say, linear predictors, as in linear regression or classification, again, we have some mild dependence on complexity parameters like the dimension of the linear classifier or the margin, and then we're able to generalize. If we're dealing with neural networks, this classical result of Bartlett and Anthony shows that as long as the size of the weights are bounded, we can generalize reasonably well. Now, granted, there's a lot more subtleties here, which I'm sweeping under the rug, that people are studying, but we are getting a growing understanding of how we think about generalization in neural networks in this IID setting. And a lot of these results have close connections to this VC notion of complexity of a fixed hypothesis class. Okay, so again, I'm reviewing the supervised learning setting because we're going to turn to reinforcement learning in a moment. But the key idea in the supervised learning setting is that given a training set, we can simultaneously evaluate the loss of all hypotheses in our hypothesis class, because we'll have some data set of images and labels, and for every way of doing a prediction, we can evaluate the empirical error of some hypothesis. Okay, so let's now turn to reinforcement learning, and let's look at the case where we don't have to worry about generalization. Okay, so let's think of a small environment, a Markov decision process. So S is the number of states. These are like these robotic states in this small toy example. A is the number of actions. So suppose we can go up, down, left, right. So there's 4 actions here, and H is the horizon that we're going to act for some number of steps and then reset. Okay, and the first result about learning that I'll survey is this really seminal result from Michael Kearns and Satinder Singh, that in basically a number of samples that's polynomial in S, A, and H, there is an algorithm which will find a near optimal policy, an epsilon near optimal policy. Okay, and the key idea of this approach is, you can't just act randomly in many settings because you might never hit this, this goal state quickly. But if you kind of combine optimism with planning, that you are planning to discover new regions of the space, you can in fact quickly find a near optimal policy. Okay, and in this stylized result here, there's no generalization because our dependence is polynomial in the size of S. So, in this like robotics, this dexterous hand manipulation example, we don't want to depend on the number of hand configurations, but in these small settings, this is okay. Okay, but the point here is that even thinking about learning in a small reinforcement learning environment is non-trivial, and there's been quite a lot of work on even pinning down the optimal minimax rates of this setting. So there's been quite a lot of subsequent work on rates in this very simplified tabular setting. Okay, but of course, what we care about is not these toy examples. We care about problems that look like this example here, Go. Okay, these are settings where the number of states is extremely large. Okay, so let's think about the analogous question of generalization and reinforcement learning. Like, what do we mean by this? Well, let's say we have a set of policies in some hypothesis class. So rather than having classifiers, we're going to have policies now. And we'd like to find a near optimal policy with, say, no dependence on the number of states, and say polynomial in the horizon, and hopefully a logarithmic in the number of possible policies. Like basically, we don't want to have to try every policy independently in the world. We like to somehow reutilize the data we have, possibly interactive data we have, to do well. Okay, and the short answer is like we want to be able to play Go without seeing every possible board configuration. Okay, so is it possible to somehow generalize with no dependence on the number of game configurations and only mildly and only a logarithmic dependence in the number of policies? And the short answer is no. That we really need, if we want no dependence on the number of states, we really need a number of samples that's exponential in the horizon if we want to be logarithmic in the number of policies. And it's easy to see why this is the case. So let's get some intuition by seeing why RL is hard. If we want to have no dependence on the number of states, just consider a binary tree. There's one rewarding leaf node, which we don't know. There's 2 to the H policies here. Okay, and if we want to find the best policy, we basically have to try every policy. Okay, and what's going wrong here? Like, what's the intuition for why this is hard compared to supervised learning? So the key here is that we can't reutilize past data. See, one policy might go down this path. Okay, now we want to try another policy. Well, it might only overlap with this, the previous paths we've seen in a very, in an almost disjoint way. See, supervised learning, once we have this training set, we can use it to evaluate every hypothesis in our hypothesis class. And that's not the case in reinforcement learning. Okay, and that really is the right intuition for this challenge of generalization, because data reuse is actually quite tricky here. I mean, we can definitely reutilize some of the data, but we can't reutilize it to easily evaluate how well another policy is doing. Okay, so so now the question is, how can we generalize? Like, maybe a representation will help. That, in the game of Go, maybe we could find a way to transform this game into some feature mapping that will make the problem easier. Okay, and we clearly need stronger assumptions to make the reinforcement learning problem tractable. And this talk is really going to be trying to get a handle on what are the representational conditions under which reinforcement learning is possible. And by that, I mean, by this, I mean, we'll have a statistically efficient algorithm, which doesn't depend on the number of, say, board configurations. Okay, and specifically the types of questions we're interested in are, what are sufficient conditions? Sorry, the types of questions we're interested in are both necessary and sufficient conditions. So there's a lot of work on upper bounds that we make lots of assumptions and then we can prove something, but we're trying to understand also what are necessary conditions and why we need to make these assumptions. Once we understand necessary conditions, we can go back and try to revisit what assumptions we need to make and think about ways to unify these approaches. And time permitting, I might even talk about how we can go about learning a representation that might be helpful in reinforcement learning settings. Okay, so we're, as I mentioned, we're really going to be talking about this problem of generalization. And more specifically, we can think about this in the context of what constitutes a good representation for reinforcement learning. Like in many machine learning settings, we think of good representations as it allows us a linear regression to work or a logistic regression to work. We'll break the talk into 3 parts, where we'll start simple, that let's just take the horizon equals 1 case. So that's really a Bandit problem, and we take out the multi-stage aspect of the problem and see what's going on. And then we'll move to trying to understand what are necessary conditions to do reinforcement learning well with regards to, say, having some representation. And then we'll move to sufficient conditions and try to understand, are there unifying ways to view how we can think about generalization. Okay, and if there's clarifying questions, feel free to ask them in the chat, and maybe Anna can jump in. I'm happy to take maybe a few discussion questions during the talk too, but we'll definitely have time near the end to go more into detail with regards to discussion points. Okay, so let's start simple and look at the horizon equals 1 case, which is really a multi-arm Bandit problem. And let's think about dealing with the case where we have a lot of actions, because see, it definitely will help us to start simple, where we get rid of the multi-stage aspect of the problem and just deal with our partial information at a horizon 1 in a horizon equals 1 problem. So this is really the multi-arm Bandit problem, which is we might be pulling a slot machine every day, and we don't know the payout of each machine. And what we'd like to do is maximize our cumulative payoff over some amount of time. And this classic paradigm due to Robbins really stylizes this exploration-exploitation trade-off. Okay, and the algorithms we obtain are very successful when the number of actions is small, but what do we do when the number of actions is prohibitively large? This comes up in sponsored search all the time, particularly when there's context. Okay, and what we do here is we're going to make some structural assumptions, which is going to make the problem more tractable. So on the left here, we have this multi-arm bandit problem. Okay, on the right here, we're going to generalize it to a linear bandit problem or an RKHS bandit problem. So think of a problem where on the right-hand side, we want to choose some decision X in some space. So our decision, say, is a real number here. And we might want to minimize this value of this function with adaptive queries. Okay, so we don't know what this function is, but every day we'll choose a value X and we'll get some noisy evaluation of this function. Okay, and here we have an infinite set of actions in this particular example. Okay, so this generalization we'll consider is this linear bandit model due to Abi and Long. And the underlying assumption, we'll generalize it to an RKHS, is that our decision is going to be xt. So it could be an add, it could be this real number. And what we're going to observe after we take our decision is some function of xt corrupted with noise. Okay, and here we're going to make the assumption that this underlying function is linear in some known features. Okay, so this is our representation as this feature mapping. Suppose we know it. And our reward is going to be linear our expected reward is going to be linear in these features. Okay, but what we reserve is this linear mapping plus noise. Okay, and in this particular case, our hypothesis class might be a set of linear functions or functions on this RKHS. Okay, so the importance of this modeling assumption now is that it gives us a way of coupling information between different actions in this feature mapping. So now we're no longer thinking of every decision as being something that has nothing to do with another decision. So the hope is maybe based on this feature mapping, we don't actually have to try every decision out there in the world to make progress. Okay, so let's see how one of these classic algorithms is going to work here, which is this linear bandit algorithm, and we can generalize it to a Gaussian process algorithm. And the idea is that this function mu t minus 1 is going to be our best estimate of the function in the past, but we're going to add some type of confidence bonus to try to gain information quickly and balance the exploration-exploitation trade-off. I think a quick video will make the idea simpler. So what we start with is, a guess of the function at the start, say, is just a line. We don't know what it is. And this gray region shows the uncertainty set. Okay, and we're going to be picking various x, and we're going to be observing a noisy value of the function. Okay, so this beta t is like a confidence parameter, and we can think of this sigma t as something to do with our uncertainty set. Okay, and the key idea of this algorithm is we're going to try to focus the exploration on plausible maximizers. So at the beginning, we know nothing, and we just pick something. This video, strange that this isn't working. Let's see. This, let me just close my
Take your time, Sham.
Keynote and reopen it. Okay. There we go. Can you all see the video now?
Yes, we can. Thanks.
Okay, great. So let me just start this again. So what we're going to see is the algorithm proceeding as it queries points. And as it queries points, it's going to gain information and change its confidence interval. It does this for a while, and note that it hones in on the right answer pretty quickly. And the key is that, we're really focusing exploration on the plausible maximizers. So this region, we haven't queried very much because we've queried here and here. So we don't have a very good idea of the function. But if you look at the confidence intervals, we don't actually think this is a maximizer because we know this guy has higher value. So we're kind of optimistically choosing things looking at the highest point of this envelope. And the idea is either we're correct, meaning we're getting high value, or we're going to gain information to shrink these regions down. Okay, and this really is a guiding principle in many of these exploration settings, which is this idea of optimism in the face of uncertainty. Okay, and what is the performance of this algorithm? So in this particular setting, the set of actions is infinite because it's the actions on the real line. And you can see in this toy example, we're doing well without trying every possible decision. Okay, and that really is based on the structure in the problem. So the regret bound here is that our performance over t steps compared to the best performance is dropping like 1 over root t, where this constant depends on some structural complexity of our feature mapping. Okay, and this is the maximal information gain. Intuitively, you can think about this as the effective dimension, that if our features are in d dimensions, then this gamma t is order dimension. Okay, so even though we're in this one-dimensional problem, our feature mapping is going to lift it to some higher dimension, and this gamma t is going to be characterizing the effective dimension, which is telling us something about the expected smoothness in the problem. So we're learning to do well at a rate that is less than the infinite number of actions in this problem. Okay, and the point now is this regret bound shows that there's a notion of generalization going on because we're doing well without trying every one of the possibly infinite set of actions. Okay, so this at least gives us some idea of what type of assumption we can make to make progress in the simple h equals 1 case. And our notion of representation is just something to do about how our actions get embedded into a space that has to do with our reward function. Okay, so again, this is in some ways pretty simple, but this model is widely used in many Bandit models with many actions, and even in contextual settings. So it's one of the basic models we use in sponsored search. Okay, so now let's look to reinforcement learning. And things are going to get a bit more tricky now, because now we're going to try to understand what are necessary conditions when we start considering the h greater than 1 case. Okay, so we've considered this Bandit problem. And now let's move on to reinforcement learning, which is like the case when h is bigger than 1. And so there's state. And we want to get a sense as to how can we do well without depending, say, on the number of states in the world or the number of actions. Okay, so let's review the Markov decision process framework, which is really the paradigm for studying these problems. Okay, so we've got this agent. The agent's going to take an action. The action will impact the environment. The environment will stochastically, our state will stochastically transition to another state, and we have some reward. Okay, and this repeats for some number of steps. Okay, so a policy or behavioral policy is a mapping from states to actions. We're going to execute a policy to obtain a trajectory over h steps. So we'll start at some state S0, take action A0, observe reward R0, transition to some state S1, and this repeats for h steps, and then we reset. So let's just consider an episodic setting. The standard definitions are the value function, which is the cumulative expected reward over h steps starting at state S when executing pi, and this state action value, which you can think of as a one-step look-ahead value, where we start at state S, then take action A, and then for the duration of the episode, we follow the policy pi. So we're deviating from the policy pi by taking A as the first step. So it's kind of like a one-step look-ahead value. We take A and see what we get. Okay, and it's, again, it's the expected value under this policy pi. Our goal is to find a policy pi which maximizes our expected cumulative reward over the episode. And let's just assume this model where we start at S0, act for 8 steps, and then repeat. Okay, so that's the basic MDP framework. If the question's about the setting, I can definitely take a question or a clarification question or two now. If not, let me jump into how we might think about generalization and what's the sort of question we want to ask here. So we mentioned early on this E-cubed algorithm where we can find a good policy, polynomial in the number of states, but we want to somehow avoid having a dependence on the number of states in the world. And one of the most natural assumptions here is suppose we could somehow approximate these Q values with linear basis functions. Okay, so that's our representation here. So suppose this Q function, in some sense, was linear in this feature mapping. And the hope is that this feature mapping, just like in this image setting, it's much smaller than the number of possible states and actions in the world. Okay, so this dimension is much smaller than the number of states and actions. Again, some context here. This is a very old idea. Like if you read Shannon's paper about having a computer play chess, it was implicit in his paper, and Bellman and Dreyfus, who were the founders of dynamic programming, they explicitly talked about using some type of Fourier representation for these features because that allowed fast computation. And there's been a lot of other work trying to understand various linear methods to approximate these state action values. Okay, and one of the most basic questions here is what conditions on this feature mapping must hold for this approach to work? And in particular, one of the simplest questions we could ask, which was really implicit in some early work by Ben Van Roy, is what if this Q function was somehow linearly realizable? That basically we're going to try to ask questions analogous to linear regression and classification. Okay, that we're going to make similar assumptions and try to see if reinforcement learning can work under these assumptions when H is bigger than 1. Okay, so I'll formalize that, the assumption in the next slide. But the idea now is like, look, having a representation and trying linear methods with this representation, this is one of the age-old machine learning approaches. And will this actually work in reinforcement learning? Okay, so the first result we'll look at here is having a linear realizable optimal Q function. So let Q star be the state action value of the optimal policy. Okay, and suppose that function is linear in, suppose that function is linear in the feature mapping phi. Okay, so this is a strong assumption, but this is basically what we assumed in this linear bandit problem when H equals 1. Okay, so we're not assuming this about all the functions. We're just saying the optimal Q function is linear in phi for every state action pair. And now the question is, if we had the features, would it be possible to do efficient RL, meaning sample efficient RL? So, we would hope to get a number of trajectories which doesn't depend on the number of states and actions. Okay, and perhaps surprisingly, it turns out that it's actually not possible. Even if you're given this feature mapping, which perfectly represents the optimal state action value, every online RL algorithm is going to require a number of samples that's either exponential in the dimension or exponential in the horizon to find a near optimal policy up to constant additive approximation error. Okay, and this is a bit disheartening because this assumption is really like the analog of linear regression, and it's really the analog of the linear bandit assumption. Okay, and what's even worse is that this result also holds even if the best action is much better than the second best action at every state. This is like a margin assumption or a suboptimality gap. So, the best action at every state is much better than the second best, which intuitively suggests we might be able to actually get the argmax policy very easily. Okay, and so it still holds under this this margin assumption, and this result here with this suboptimality gap was really extending this result of Wise, Imotia, and Chaba recently, and I view this result here also as really a breakthrough result. So they first showed this without the suboptimality gap, and this result somewhat simplifies the construction. And I view this here as this is just resolving one of the most basic questions we can ask, because this is like the baby model. We want to understand if reinforcement learning is possible under assumption, and it really isn't. And it took quite a lot of time building up to this result, but it's this question arguably goes back to the 50s. Like, is reinforcement learning possible with a linearly realizable Q stars? Okay, and it turns out this result also holds.
If I can ask a quick question, what is the intuition behind the proof of this theorem? Is there some way to see why?
Oh my God, yeah. So this is I'll show you a figure in a moment. It's somehow the intuition is that as you the error somehow amplifies. So if the horizon is 1, you do well, but not perfectly. Okay, and somehow that little bit of error somehow just keeps amplifying because you haven't found the right policy, and it amplifies. Okay, and that's why this gap assumption is somehow surprising, because the gap assumption kind of suggests that H equals 1, you might be able to exactly find the right optimal policy. But you kind of can't visit all the states easily, and your errors amplify. But this is kind of why I view this Wise result as a breakthrough result, because there's so many subtleties here. And I think a number of us have been working on this for such a long time to try to build intuition. And we really didn't know if there was some clever upper bound versus a lower bound. So it's definitely subtle. But I'll have you to chat about it more. But it's an issue of how errors amplify in reinforcement learning, and theoretically, at least theoretically, it's very real. Okay, and it turns out the result also holds for a linearly realizable pi star. That even if pi star is representable as like an argmax policy of the feature space, you get the same result. This result is a bit easier to prove, and we actually proved this one before the other one. And this result also holds if there's a margin on the optimal policy. So taken jointly, at the H equals 1 case, this is really the analog of Bandit regression and classification, and everything's fine with horizon 1. But as the horizon increases, things become exponentially harder in the horizon. And this is just a picture showing the construction, but I won't really discuss that now. But at some level, this is a bit disappointing that it shows that linear realizability is simply just not strong enough to do reinforcement learning. And the positive side of this, I think this starts explaining why we're making such complicated assumptions for upper bounds. Before I go to the upper bound, I just want to make a quick point that Anna's question was like, what does this construction look like? And it's a crazy construction. I mean, I think it's elegant in a lot of ways, but it's definitely quite sophisticated. And and the question when you look at lower bounds is like, look, is this reflective of practice? You can come up with some crazy worst case example, and maybe in practice we don't care. But I'd argue that reinforcement learning practitioners really do know that this error amplification issue is very relevant in practice. So here's just a quick simulations in a slightly different setting of offline reinforcement learning that you can prove a similar result. Let me just pause these videos. So this is a setting where we come up with a good representation, say with some online training. And we create a data set by mixing a running policy. So it's an offline data set with just a random policy. So we mix data from trajectories from these two things, and we try to do policy evaluation. Okay, so again, I'm not going to go too many details in this, but just kind of coming up with an offline problem where we have data from the policy we care about, which is this running policy, and some data from a random policy. And now the goal is to evaluate this policy, the running one. And the features we're going to use is actually going to be features from a pre-trained neural network to evaluate this policy. So these are very good features. And when you mix the data from these two, we actually see error amplification when you try a backup-based method. So there's been, for some of you studying this, been really a ton of work in offline learning because we have tons of offline data and we're trying to do policy evaluation. And we do it, we actually see these error amplification effects. And what we're arguing in this work is that even if your representation is good in that it can capture the policy we care about, you will see error amplification. And I think these theoretical lower bounds are really capturing these amplification effects we see in practice. And one of these issues is in what Rich Sutton calls the deadly triad, but somehow the intuition for these lower bounds is that it's very easy to get error amplification in reinforcement learning, and on top of that, it's very relevant in practice. Okay, so the meta point for this slide is really just that these issues are very relevant in practice, that we do in fact see error amplification. Okay, so now in the remaining time, given that we have this somewhat disheartening result, that linear realizability is not enough to do efficient RL, we can ask what does suffice to do efficient RL. And this, again, might lead to some practical insights. And we might ask, like, is there a common theme to the types of assumptions we have to make to get RL algorithms to generalize? Okay, so now we're going to move to the positive results. Again, our question here is really analogous to supervised learning, that we'd like to find a near optimal policy, an epsilon near optimal policy, with no dependence on the number of states or actions, or maybe forget about the number of actions. We just don't want to have any dependence on the number of states, and a sample size that depends polynomial in the horizon, our accuracy parameter, and some complexity measure of our hypothesis class. Okay, and the first result I showed is that for the best in class F, we can't do that. That was this sort of trivial binary tree example. And the second thing, which was pretty disappointing, is that for linearly realizable Q star or linear realizable policies, we also can't do this. Okay, so where does this leave us? Well, as putting theory caps on, we always know we can solve problems. If you just keep smacking down more and more assumptions, you can solve it. But we're trying to get an understanding of the nature of the assumptions we have to make. And this result here is already giving us intuition that the types of assumptions we need to make are likely going to look more complicated, because this is kind of like the baby assumption that we would hope that things work, and it doesn't. So there's lots of special cases of models where people make various assumptions, and you can prove that RL is possible under these assumptions. One of them that we're going to pay particular attention to is this linear Bellman completion assumption. But our question here is, are there somehow commonalities in the types of assumptions we need to make to get reinforcement learning algorithms to work? Okay, and there are some, but they don't cover all these cases. So another breakthrough result from a couple of years ago was this Bellman rank assumption, which captured many of these models. The paper at the time was overlooked, but now people really understand why this assumption is so fundamental in capturing these models. Okay, so, but it doesn't capture all of these models. But the overarching question is, how do we start thinking about the space of sufficient assumptions, because we've ruled out the kind of baby case? Okay, so to get some intuition, let's look at a very intuitive special case, that of linear Bellman completion. So this is a special case where generalization is in fact possible. Okay, so suppose our hypothesis class is linear, that like before, we're going to consider a set of linear functions for the q's. Okay, so we're going to say Q of F is some linear mapping on our features. So I'm just overloading F with W. So F is some hypothesis. It has corresponding weight vector W. Okay, so that's the linearity assumption. But now we're going to make a much stronger assumption. We're going to say our hypothesis set is complete if it's closed. You should have called this closed. The literature, sometimes they call it closed, sometimes they call it complete. But what we mean by this is F is closed under Bellman backups. So if you do a Bellman backup to the Q function, it remains in the class. And remember, Bellman backups are this kind of one-step greedy look-ahead approach. So if you start with a Q, T of Q, which is the Bellman backup, is the value where you follow A and then take the greedy action after that. Okay, and this value iteration algorithm is just applying Q repeatedly. And remember that the Bellman optimality equations say that Q star minus TQ star is 0. Okay, so this completeness assumption is somewhat natural, because it's saying if we start with a Q, apply T to it, it stays in our hypothesis class. Okay, so it does feel intuitive. So we could have said, why do we start with the linear Q star? The point here is that Q star is a very strong assumption. Sorry, this completeness is a very strong assumption. Okay, and why is it strong? Well, one way to view why this is strong is if you add a feature to the existing features, you could break this completeness property, because when you add a feature, maybe it's no longer closed under T. Okay, and if you start looking into it and trying to say, well, what types of features hold, you start realizing that the types of hypothesis spaces where this assumption holds really do fundamentally capture properties of the underlying dynamics. So it's kind of interesting here that this assumption which permits sample efficient RL, means we actually have to capture some structure in the world, because this T somehow intricately is connected to how the behavior of this dynamics model P. Okay, and I'm just going to state a technical property which is helpful in understanding why sample efficient RL is possible with linear Bellman complete classes. Okay, so a key property we discussed early on is that of having being able to do data reuse. Okay, and with hypothesis class that are linear and closed, it actually turns out there's a very similar data reuse property that we can utilize, analogous to the linear Bandit setting. Okay, so this is a technical statement, but it's pretty intuitive, which is if we look at the Bellman error of one of these hypotheses, and under any pi. So pi is just any policy. We look at the expected value of the Bellman error, which is Q minus R minus V. So V is the greedy thing under Q. So that's literally just the error of Q minus TQ in expectation. Okay, we look at that, and this expected value under any other policy is upper bounded by a linear function. So by T of W, I just mean the corresponding weight vector when we back up Q. Okay, so this looks a lot like the linear Bandit assumption. And what's the intuition here? The intuition here, yeah, one sec. So the intuition here is that for any policy pi, we get a constraint. We can evaluate the Bellman error of a function f. Anna?
There is some question from the audience which looks like a clarification question, so I just want to read. Is the Bellman rank a somewhat general notion to rank? If it is there something in reinforcement learning that is similar to implicit regularizations in supervised learning, where rank also plays an important role? Can you comment on that?
Um, uh, so I didn't understand the first part of the question. So is Bellman rank similar to what? The very first sentence?
To a notion of the rank. Raquel, can you allow Bolundai to speak?
Or is it typed? I can just look at the.
Yes, it's in the chat.
Okay, let me just look at the chat. Okay, well, maybe I'll come back to this a bit later. I'll just spend a couple of points on it now. So okay. It isn't really related to sort of implicit regularization. So this Bellman rank assumption is, it's pretty subtle. It basically, for now, just think about the Bellman rank as being analogous to this linearity assumption. It's a condition where if you look at the Bellman error of some hypothesis F, when you use another Roland policy pi, it's linear. Okay, and what's nice about this assumption is that since this holds for any pi, so suppose we execute some policy pi. This means for every possible hypothesis, we can get this expected value. Okay, and that's, Bellman rank in a sense is a generalization of this. Well, it's basically this condition. Okay, and so I'll come back to your question later on, but it isn't really related to implicit regularization. It's more like a condition related to saying that the Bellman error, the expected Bellman error has a linear structure to it. Okay, and if you have this linear structure to the to your Bellman error, then efficient RL is possible. Okay, and given time constraints, I'm not going to go too much into this bilinear, the strict definition of a bilinear class, but I was trying to, the question we were asking before, is there a way to somehow unify a bunch of these different modeling assumptions? And there's a way to generalize this notion of Bellman completeness for any hypothesis class, where the basic idea is that the expected Bellman error has, under the same corresponding policy, has a linear structure. And we have access to some kind of discrepancy function where we can estimate these inner products. Okay, so we can view this as a generalization of the Bellman completeness assumption. And I think I'll let people look at this offline because it does take a while to grasp this concept, but I will just highlight where things stand in terms of an overview, because I think this picture will start to give people a sense of what's going on. So these boxes in blue are kind of named special cases that people have showed we can do provable RL. Like we know some of them, like linear quadratic regulators. This is the control model. There's block MDPs. There's various named models which various people have showed we can do provable RL. So this Bellman rank was the first such assumption which gave a structural characterization. This Bellman completeness is this box here. That's the one I just started with and gave you an explicit characterization of. And this recent concept we had really shows how to generalize this notion of Bellman completeness, which basically captures all kind of almost all known models where we can generalize. And it basically amounts to, you can really think of this as a generalization of how to think about Bellman completeness. But the point is, it's giving structural constraints on this feature mapping, which permit efficient, sample efficient RL. And it works for model-based methods and model-free methods. Okay, and formally, this picture is correct, that basically all of these models here are captured on this bilinear class framework. The only one we don't know how to do is this one special case, which you can see the paper for. And I should also mention there's another notion which captures some of these based on the Bellman-Eluder dimension. The one concern with this model is we don't know of any natural models sort of in this region where this thing captures something more general than what's captured here. But the structural notion of bilinear classes is really a way to think about the natural way of generalizing this Bellman complete notion, and it captures all known settings where sample efficient RL is possible. Okay, and given the time constraints, I'll just mention the theorem with regards to the upper bounds is that, for any of these models in blue, we have this meta theorem now that with a number of samples that's basically polynomial in the information gain, we can find an epsilon optimal policy. Okay, and here this information is exactly the same gain as in the linear bandit setting. So the meta point here is that the settings where generalization in RL is possible are really just stronger assumptions where the RL problem can be made to look very much like the linear bandit problem. And the complexity of RL just has to do with the information gain of this underlying feature mapping. So for example, for the linear Bellman completeness setting, the complexity depends on the information gain of the of your feature mapping. So it really is a generalization of the linear bandit setting to the h greater than 1. And it's definitely a much stronger assumption than the linear realizability, but we know it's necessary. Okay, and the idea of the algorithm is it's basically a lot like a generalization of the linear UCB. So for Bellman completeness, what you're going to do is you're always going to be optimistic subject to some constraint. Okay, and the constraint is really going to be, you're going to be optimistic subject to the constraint that you try to keep the Bellman error small on the data you've seen. Okay, so it really is the same principle of optimism in the face of uncertainty. And when we gain new information, we're just going to use that to further constrain our hypothesis space. Okay, so before wrapping up, I'll just briefly mention a question of what do we do if we don't know the features? So, we looked at this result that if we had a hypothesis class that was complete in this Bellman completion sense, then we can do things, then we have a provable algorithm. Okay, and most of these other settings I mentioned, we have to know the feature mapping. But what if we don't know the feature mapping, say in this Bellman complete setting? Okay, so there is one recent result we have where it again falls under this bilinear class setting, but it's a setting where we can actually learn the features in a precise sense. Okay, and I'll let people look at the paper for the details, but the algorithmic idea is pretty interesting because we're doing the exploration not just to gain rewards, we're doing exploration to actually help us learn a representation of the world. So we're actually kind of exploring to try to find regions of the world where we don't understand what's going on, and we're learning a representation based on the dynamics in the world. Okay, so this is one setting where we can actually both simultaneously learn the representation provably and do RL. But these assumptions for it to work are substantially stronger than what we have in supervised learning. Okay, so I'll just wrap up now and highlight some of the main points that I think we've clearly understood now why the theory of RL is fundamentally different from supervised learning, because we can't do agnostic learning, and linear realizability is just insufficient for RL. We need much stronger assumptions. And once we understand that, then we see why once we start looking at upper bounds, things are a lot more subtle, because we have to make significantly stronger assumptions, but we have a unifying way of starting to look at some of these stronger assumptions. And I highlighted this one case falling under this framework where you might be able to learn the features. And finally, what's interesting about reinforcement learning, both from a theoretical and practical perspective, is these issues are very relevant, that error amplification comes up all the time in reinforcement learning, and we are looking to find ways to build better exploration algorithms. And I'd like to thank a number of super talented colleagues over the years, and I just want to highlight 3 students right now, since they've done a lot of the work. So Rusang Wang's been collaborating with me for quite some time. and Yunhao Wang was involved in some of the proofs of the lower bounds, and Gaurav was a student at UCSD involved in proving a number of these upper bounds with regards to bilinear classes. So, so thank you very much, and I'm happy to take some more questions.
Thank you. Christopher has a question. I'll ask allowed to tell. Okay, Christopher, go ahead.
Unmute. Can you hear me?
Yes.
Oh, great. Okay, this is Chris Musco. Really nice talk. So like this, I'm interested in this example you found where like that amplification seems to be a very real problem in the running task. So I guess we know that that's a case where you have this linear realizability, because like that at some point someone learned that policy from these like deep learned features. But is the idea that this falls outside of this like stronger Bellman rank class or this complete class, or is it that just like you need a different algorithm to attack that problem?
Yeah, so right, so let me summarize the question and go back to great. So this is a yeah, this is a really nice question to try to get a handle what's going on, because these issues are much simpler in, so let me just summarize the question and the offline setting. So so in the offline setting, so we're going to have a data set, and the analogous theory claim for offline learning, in a sense, it's much simpler here. So the offline claim is going to be, forget about policy improvement. Let's just suppose we want to evaluate a given policy. So we're given a policy and we just want to evaluate its performance, and we're told the policy's value is linear in some features. Okay, and suppose we also have coverage in a spectral sense. So like the observational data we have has like well-conditioned covariance matrices of the features. Okay, so H equals 1, this is linear regression, we're done. That makes sense? Okay, and the most natural algorithm is to do backups.
Sure.
Okay, and so the upper bound shows, it's an information theoretic one, that if you have a well-conditioned matrices at, in your data, and you have linear realizability, statistically, you need 2 to the h samples to estimate the policy. Okay, so it's not just for the backup algorithm. Okay, and this is a little surprising because linear regression works at every level if you have the right targets, but the errors amplify. So that's what goes wrong with the linear regression algorithm. But this lower bound shows every algorithm fails. Okay, and now I'll say that, in practice, what did we do here? Well, we actually took a representation that was trained with online data for this running policy and ripped it out and tried it with backups with this offline data, just mixing in some extra data, and it explodes. Okay, and so that's sort of the setting. And one of Chris's questions in there was, what's going on with, say, the linear Bellman completeness in the setting? Okay, so the analog of linear Bellman completeness here is it's a stronger assumption, which clearly isn't holding. So what linear Bellman completeness is saying is, after we do a backup for any function W, the next thing we want to back up is still in the class. Okay, see, basically that's going to prevent error amplification, because it's saying, suppose we do a backup at the last stage. Okay, then we do one step above. The completeness assumption says that the next function we want to back up lives in the class. So basically, you can kind of back up the errors. So if you really were complete, that would not happen here. But what's showing here is, these pre-trained networks are not giving us representations which can somehow back up every value function. So, and this is a very real effect, that your errors just, start amplifying as you keep doing backups.
Yeah, okay, interesting.
So, yeah, because somehow, like, see, once you've backed up something at the last stage, you don't have the correct weight vector anymore for the last stage. You have a little, and if the next regression, so basically you have a new regression target, And as long as, you could approximate this new regression target, things would work. But that really is a much stronger assumption on your features. And that does not seem to happen, at least if you just grab some pre-trained representations.
Yeah, interesting. Huh.
Now,
my apologies. I couldn't.
Now, that isn't to say that offline RL will fail, but it does say that the way we learn representations can't just be in this error-driven manner. It's almost like we want to learn features which are robust to Bellman backups, which is a kind of a very different feature learning approach.
Yeah, okay, thanks. Makes sense.
Do we have any more questions? I see somebody is waiting. Okay, Mariam. Mariam, you should be able to talk now.
Yes, hi. So I want to know what's the relationship of this strong assumption with practical settings? And also, can we still get like similar bounds with less strong assumptions, or do we have proofs that we can't? So these assumptions are kind of necessary.
Right. Okay. So the first question was the relation of this assumption to practice. And your second question was with regards to, sorry, what was your second question? This was.
So can we prove that these assumptions are necessary, or can we still try to get similar bounds with less strong assumptions with?
Right. Okay. So the first question was with regards to these assumptions in practice, like why might they hold? And for those assumptions, you're referring to the linear realizability assumptions?
Yes, the bilinear class. And
sorry, the bilinear class. Okay. So right. So good. So the lower bounds, in a sense, that's kind of like the baby assumptions. Like in this offline thing, it's like we want to evaluate a particular policy. A representation can perfectly capture the value of the policy. So that seems like the minimal thing you might want, and that we know is not possible. So now the question is, this bilinear class assumption, or say Bellman completeness, how does that relate to practice? And can we relax it? So in a sense, these experiments are showing that at least some settings, we tend not to learn these features automatically. So in other settings, we might actually have features which are closed under backups, but I think this is a very good question that, can we learn such features? Because the idea, like for linear Bellman completeness, that we have this closure property, if you just look at value iteration, this is very natural. It's just somehow saying that at every step of value iteration, you can project back perfectly in your class. And what this assumption is actually showing is that, at least in some settings, this doesn't happen. So specifically what we did here is we took our features from an online training method of this running policy. So we actually did something adaptive, found the features, and took them out. And we didn't get, and it doesn't work when we do backups. And that kind of shows that we actually are not finding the features which satisfy the linear Bellman completeness setting or this bilinear class assumption. So so this is why I think this is, actually you asked during our earlier discussion, sort of what are open questions. So I think one question here is like, actually, how do we learn such features which satisfy the assumptions we need for RL? Because sometimes RL works and sometimes we get these error amplification effects and we don't really know when we're getting the representations which support RL. So there's, the short answer for your first question is, we don't know if we're going to get the representations we need for RL, and we have plenty of empirical evidence that it doesn't just happen naturally. So So I think this is a pretty interesting question of like, how do we actually get representations which make RL stable? And the second question, is this bilinear thing necessary? Well, we don't really know, because we know if we relax it too much, we can't do it, because then we're back at linear realizability. And if we start like adding assumptions, there's reason to believe that we just don't know, right? It's sort of asking the question, is there something in between the things we know how to do and the things we know that are impossible? And so I think that's I think this is an interesting question, and we've been thinking about it for a while, but it is pretty natural to have things like the Bellman completion assumption. So
okay.
definitely.
I think we may have one more question from Hack. Sorry, I didn't want to lose his question.
Hi. So my one question is, what's the main difficulty in putting the near deterministic linear Q star in like with any of the other MDP classes in that plot?
Right. Okay. So it's a great question. Let me repeat the question. So we'll go back to going back to this figure. Kind of all of these known models fall in this bilinear class assumption, which we could view as a generalization of Bellman completeness. There's this one outlier here, okay, and I'll explain what this outlier here is. So this is the assumption. We're going to go back to this assumption where Q star is linear in some known features. Okay, but let's make the further assumption that the dynamics in the world are deterministic. Okay, so that's what deterministic linear Q star means, that there's no stochasticity in the dynamics. Again, if you have that, the claim is you don't have any error. Okay, so why is this possible? First, it's possible because the world is deterministic, you have no errors in your regression. Like you're basically solving linear systems perfectly. Okay, and when that happens, you kind of get no error amplification, and this algorithm works. Okay, so now we're gonna just setting the stage for your question, and the question I heard was that we're kind of asking what's the difficulty now and why this class doesn't live in this class. Okay, and the reason this is working is really due to a different reason. It's somehow that the properties of this framework are such that you don't have error amplification when you do backups. Okay, so these classes somehow are stronger in that you are making more global assumptions, like this completeness assumption. Okay, that's more of a global condition that says everything in the class, you're saying how it behaves. Okay, what's making this model work out is that when you use something close to the right answer, your errors don't amplify. In fact, you have no errors at all, but it can be weakened to assumptions where your errors don't amplify. And so far, we don't really know how to combine these this class into this class. Okay, and the only settings where this seems to work are either settings where the dynamics are, nearly deterministic, or, and we have oftentimes big gaps. So I think it's an interesting question, but the intuition is, just somehow it's a different reason as to why this algorithm works. And that's why it lives outside. There's actually one more case that lives outside of this class that you can see in the paper. But it's again due to this low amplification condition.
Thank you.
We will have to wrap up because you're going to have another meeting in 10 minutes. Thanks again so much, Sham, for giving a talk. It was an excellent talk. And you will stay with us for the meetings. Thanks a lot.
Yeah, thanks, Anna. Thanks, everyone.
Bye.